All right, so we're going to be solving problem 2.49, which says a sphere of radius r carries a charge density rho equals kr, where k is a constant. Find the energy of the configuration. Check your answer by calculating it in at least two different ways. So the book gives us two different equations to check this, but you just have to know that the energy of the configuration is equal to the work. So the first equation, we can say work is equal to epsilon naught over 2 times volume integral of the magnitude of the electric field squared. The second one is 1/2 times the integral of the charge density times your potential d tau. So either way you do this, you're going to need to know the electric field inside and outside the sphere. So that's going to be our first job. So we'll say that this is region 1 inside and region 2 is outside. So to do this, we're going to use Gauss's law to find the electric field, which says the electric flux through a given area is equal to a charge enclosed divided by epsilon naught. Now, regardless of where you draw your Gaussian surface, whether it's on the outside here or on the inside, either way, you can just say that the radius is little r. So for both region 1 and region 2, the left-hand side of Gauss's law is going to be the same. So from this, we can make a symmetry argument and say if you take this little portion of the charged sphere here, this section right here creates a contribution to the electric field pointing this way. This one creates a contribution pointing this way. And there's, one pointing out that way as well. And it's clear to see that these two components, their tangential components, will cancel out, leaving only this portion here pointing out in the radial direction. So from that, we can say that the electric field is in the r hat direction. Likewise, we can say that because this is a fixed area, or this is not a fixed area, this is a fixed radius of little r, that the differential area element is going to be r squared sine theta d theta d phi, and that is also in the r hat direction. So E dot dA is then going to be equal to ER squared sine theta d theta d phi, where ER squared is a constant. So then we can go ahead and do our integral. We can pull out the constant, say ER squared. We'll be integrating from 0 to pi of sine theta d theta, and that's because there's that angle theta. We're going from 0 to pi, times the integral of 0 to 2 pi of d phi to go around the circumference of the circle. So looking at this, we can clearly see that this will be phi evaluated from 0 to 2 pi, which is just equal to 2 pi. With this one, we can see that this will give us minus cosine theta from 0 to pi. Minus cosine of pi is going to be minus -1 minus negative from the negative cosine. Cosine of 0 is 1. So this will give us 2. So we get 2 and 2 pi, multiply those together, you get 4 pi. So we can say that this whole section right here is equal to 4 pi. This integral, or these two integrals, will come up many more times, but to save time, I'll just cut straight to it and say 4 pi, so I don't have to go through that every single time. So we can then say that the left hand of our Gauss's law gives us ER squared, or actually, here, it'd be better to write it like this. Magnitude of the electric field times 4 pi r squared, which makes sense because 4 pi r squared is the surface area of a sphere. So the next part is going to be moving into region 1. And that is going to be where the electric field, actually, why don't I just call it E1. And that is for R less than big R. So moving into the right side, we're going to be doing the Q enclosed over epsilon naught, which does depend on the size of your Gaussian surface, how much you have enclosed. So first we're going to be doing inside the sphere. So Q enclosed over epsilon naught is equal to 1 over epsilon naught times the integral of your charge density d tau. Now, this, as we know, rho of r equals kr, and d tau is going to be equal to r squared sine theta dr d theta d phi. So, rho d tau is then going to give us kr cubed sine theta d theta, or not d theta, dr d theta d phi. Okay, so to write out the integral, we can pull out some constants, which is just the k and the epsilon naught for now. Say k over epsilon naught times the integral from 0 to r. This is because we're assuming that our Gaussian surface is a small circle of radius little r inside the bigger radius of big R, of r prime cubed dr prime. The integral from 0 to pi sine theta d theta is the integral from 0 to 2 pi of d phi. Now, as I mentioned before, we know this section will give us 4 pi, which is great. This section here will evaluate to r prime to the 4th over 4, evaluated from 0 to r, which just gives us r to the 4th over 4. So, from that, we get k over epsilon naught, r to the 4th over 4 times 4 pi, which then becomes, of course, k r to the 4th pi over epsilon naught. Now that we have this part, we can equate the left and right hand sides of Gauss's law to actually solve for the electric field vector inside. So, say E 4 pi r squared is equal to k over epsilon naught r to the 4th pi. Cool. So then we can start just canceling things out. That'll go away. That'll go away. That'll go away. This will become a 2. And what we will be left with is that our electric field in region 1 is equal to k over 4 epsilon naught r squared, and it's in the r hat direction. Sweet. Now moving on to region 2, which is for little r greater than big R. Same process. So actually, the only thing that'll change here is your bounds of integration on this integral right here. So actually what I'm going to do is I'm just going to go and snag this whole bit. And just move it right down here. There we go. And I'm just going to go ahead and change these bounds of integration. That doesn't need to be primed anymore. We'll say from 0 to r of just r cubed. Everything else still holds. The only thing that will change is our bounds of integration. So this will then evaluate to r to the fourth over 4 from 0 to big R, which is r to the fourth over 4. So now we have k over epsilon naught, r to the fourth over 4 times 4 pi, which equals k over epsilon naught, r to the fourth pi. Now we'll just go ahead and do the same thing that we did with the last one and equate it to the left-hand side of Gauss's law. So we can say e 4 pi r squared is equal to k over epsilon naught r to the fourth pi. Now in this case, all that cancels is the pi, and you end up getting that the electric field vector in region 2 is equal to k over 4 epsilon naught r to the fourth over r squared. And this is also in the r hat direction. So now that we have our electric field vectors, we can go ahead and use method 1. Method 1, remember, was this one, where we squared the electric field vectors. I'll just go ahead and say method 1. So the way that this is going to expand is like this. Work is equal to epsilon naught over 2. Because we have two different electric fields, it will integrate over both of them separately and add them together. So it'll be like just like that. And to make our integrals just a little bit easier, or easier to see anyway, E1 squared is equal to k over 4 epsilon naught r squared quantity squared, which is equal to k squared over 16 epsilon naught squared r to the fourth, where this whole thing is constant. So then we can say E1, or the magnitude of E1 d tau, or squared, is going to be equal to k squared over 16 epsilon naught squared times r to the sixth sine theta dr d theta d phi. And actually, you know what? I'm gonna rewrite this just a little bit different. I'm gonna say r to the sixth dr sine theta d theta d phi. And we already know that integrating over this is going to give us 4 pi. So to write out the terms for the second one, E2 squared is equal to k over 4 epsilon naught times big R to the fourth over little r squared. And that whole quantity squared, which is equal to k squared over 16 epsilon naught squared times r to the eighth, big R to the eighth, times 1 over little r to the fourth. So then E2 squared d tau is equal to k squared over 16 epsilon naught squared r to the 8th times 1 over r squared, because the r squared that comes from that d tau will cancel with r squared on the bottom. 1 over r squared dr sine theta d theta d phi. Just like that. So, as you can see, both have these constants, so we can go ahead and factor them out when we're writing the full integral. So you can say the work is equal to epsilon naught over 2 times k squared over 16 epsilon naught squared, where right away we can see that cancels, and that will be multiplied by the integral from 0 to r. These bounds are important, actually. I'm going to write them in yellow. From 0 to r of r to the 6th, because this is E1, this is inside the sphere. So we're going from 0 to r, and then the next one will be r to infinity. dr. And then, I'm just going to go ahead and write that the integral of sine theta d theta from 0 to pi times the integral of d phi from 0 to 2 pi. We know I'm going to go ahead and just write that out so you know what I'm doing, but then I'll erase it, and I'll say that that is just times 4 pi. Because we know from doing it previously that that's what we'll get. Plus r to the 8th, big R to the 8th, times the integral from big R to infinity of dr over r squared times that same thing, 4 pi, from the integral of sine theta d theta and the integral of d phi. That gives us the volume. So we can go ahead and factor out the 4 pi, which will end up giving us, and also deal with the 2 out there as well. This will end up giving us k squared pi over 8 epsilon naught times the integral from 0 to r of r to the 6th dr plus big R to the 8th times the integral of big R, or from big R to infinity, of dr over r squared. Okay, now to go ahead and evaluate these integrals. This one right here, the r to the 6th, we know that this is going to be r to the 7th over 7 from 0 to r, big R, which is going to give us big R to the 7th over 7. Now, the second one is going to give us, actually here, let me write it out like this. The second one is going to give us r to the 8th times minus 1 over r is the integral of 1 over r squared. That's evaluated from r to infinity. Plugging in at infinity, you get 0. 0 minus negative 1 over big R, you just get 1 over r. R to the 8th times that will just give you r to the 7th. So you'll end up getting big R to the 7th over 7 plus big R to the 7th, which equals 8r to the 7th over 7. Now we can plug that back in here and account for this constant and say that using this method, work is equal to k squared pi over 8 epsilon naught times 8r to to the 7th over 7, which is equal to k squared pi over 7 epsilon naught r to the 7th. And we'll go ahead and box this because this is correct. So boom, that's our first method done. Now the second method, before we can continue, we have to find the potential inside. So method 2, if you recall, is work is equal to 1/2 charge density times the potential is d tau. So, as we know, the potential is equal to negative integral, path integral, E dot dl. And we can break this up into the two regions. So, working inwards from our reference point, this is from a reference point of infinity to some point, we'll just say that's r, or I'll just say a for the general form. Break that up into two regions, outside the sphere and inside the sphere, because they do not have the same electric field. So it's going to be minus infinity to r of, and oh, actually another important note, this dl element is going to be dr. It is going to be dr r hat. So electric field vector, as we said, is E r hat, and dl is going to be equal to dr r hat because we are working inward radially. That is our path. So we'll end up getting E2 dr minus the there should be a vector there, minus the integral from big R to little r of E1 dr. Just like that. So you can go ahead and do this piece by piece. The first one of integral of, the potential in region 2, so outside the sphere, is going to be equal to minus integral from infinity to big R of kr to the 4th over 4 epsilon naught r squared dr. We can pull out the constants, of course, but this will end up evaluating to minus kr to the 4th over 4 epsilon naught times minus 1 over r, which is the integral of dr over r squared, evaluated from infinity to r. In this case, plugging in r, you'll end up getting minus 1 over big R minus 0. So this will give you k r to the 3rd over 4 epsilon naught. And I'll go ahead and rewrite this as 3 over 12, which is the same as 1/4, times kr cubed over epsilon naught. Now, the second integral is going to be the negative integral from big R to little r of k, or that's not k, and then we'll say r prime squared, dr prime over 4 epsilon naught, which is going to end up evaluating to negative k over 4 epsilon naught times r cubed, r prime cubed over 3 from big R to little r. Little r is just some arbitrary distance away from the origin in this case, which is equal to minus k over 4 epsilon naught times little r cubed over 3 minus big R cubed over 3. which is equal to minus kr cubed over 12 epsilon naught plus k big R cubed over 12 epsilon naught. So that's why I put this in, so that they could have a common denominator. So from that, we can add those two potentials together. Actually, I'll just go ahead and say that this is like V2 and this is V1. So we can then say that our total, V of R, is equal to 4k R cubed over 12 epsilon naught minus k little r cubed over 12 epsilon naught, which is equal to k over 3 epsilon naught times big R cubed minus r to the third over 4. Yeah, yep, that works out. Yes, okay. So now to actually apply the method for finding the work. So of course, work equals 1/2 integral rho times our potential, which we just found, d tau. And this quantity is equal to kr, which is the charge density, times k over 3 epsilon naught times r cubed minus little r cubed over 4 times r squared sine theta, actually, r squared dr sine theta d theta d phi. So this actually ends up simplifying to k squared over 3 epsilon naught times big R cubed, little r cubed, minus little r to the 6th over 4. And again, we're going to say dr sine theta d theta d phi. So now we can go ahead and just integrate and say work is equal to 1/2 times k squared over 3 epsilon naught. We're just pulling the constants out here. And that is times the integral from 0 to big R, which is our charged sphere, of big R cubed, little r cubed, minus little r to the 6th over 4 dr. And then again, as I did earlier, that integral from 0 to pi of sine theta d theta, and integral to 0 to 2 pi of d phi is just going to give you 4 pi. So this part right here will end up getting r to the third times little r to the fourth over 4 minus little r to the 7th over 28 from 0 to big R, which is then equal to 7 times big R to the 7th minus big R to the 7th over 28, which of course is equal to 6 big R to the 7th over 28. So now we can go back up here and plug in and incorporate our constants and say k squared over 6 epsilon naught times 6r to the 7th over 28 times 4 pi. Here we can see that the 6's will cancel, like there, and the 4 and 28 will reduce to a fraction of 7, leaving you with pi k squared r to the 7th over 7 epsilon naught. And that is correct, thus proving that regardless of which equation you use, here's that one, and here is the same one. Regardless of which method you use, regardless of which of these you use, you will get the same energy for the energy of the configuration. Thanks so much.